Perfect. So, good morning, everyone, and thank you for joining us. As Sharif said, my name is Konstantinos Iotinis. I'm a strategy and growth specialist at DTE, and I'm joined by Jacob Roskop, who's an engineer 3 at EPRI. You can see us in the next slide. And together, we've been working closely on a joint initiative to explore how battery degradation and its modeling can inform smarter augmentation strategies for grid scale energy storage. Now, this collaboration brings together DTE's operational experience and EPRI's analytical capabilities to tackle a challenge that has been becoming an increasingly important thing as utilities scale their storage to support renewable integration. Now, we are excited to share our findings with you, and we hope they spark some ideas about your own projects and their planning. And let's move to the next slide. We'll do a quick look of what we'll be covering today. So we'll start by setting the stage with the importance of energy storage and the challenges that are posed by battery degradation. From there, we'll talk through the collaboration between DTE and EPRI and how we structure the project to address these challenges. And then we'll introduce the tools we used, specifically Storlytics and derivative for dispatch optimization, and show how they informed our augmentation strategy. We'll also explore the financial implications of different approaches and share some practical applications that can guide future planning. And finally, we will wrap up with some key takeaways and conclusions. Let's move to the next slide. So before we dive into the more technical aspects of our work, I want to take a moment to introduce DTE Energy. We are a Michigan-based investor-owned utility, and we're headquartered in Detroit, serving millions of customers through our regulated and electric and gas utilities, as well as several non-regulated business units. And we are vertically integrated, which means we manage our generation, distribution, and customer service. We don't own our own transmission system. We are part of the Mid-Continent Independent System Operator, or MISO, which plays a key role in our grid coordination. Historically, we've been very coal heavy, but we're undergoing a major transformation. So we're committed to delivering cleaner energy for Michigan, and that commitment is shaping how we invest in new technologies, and that includes energy storage. Now, Michigan has set some ambitious targets, a 60% renewable portfolio standard by 2035 and a 100% clean energy standard by 2046. And these targets are driving our investment in renewable and storage across the state. And the next slide, we'll see our projected energy storage build out through 2042, which is aligned with our own DTE Clean Vision IRP and Michigan's broader clean energy legislation. And you'll see that we'll target about 780 megawatts of storage by 2028, scaling up to about 1.8 gigawatts by 2042. And this includes both DTE-owned assets and third-party capacity secured through tolling agreements. Now, it's notable that under Michigan's 2023 PA 235, which is the Clean Energy and Climate Action Package, the state has set about a 2,500 megawatt energy storage target by 2029, and we're expected to deliver roughly half of that, which I think underscores the scale and urgency of our commitment. For that, we've already closed an RFP for a portion of the capacity, and we're actively planning some deployments like the Trenton Channel and the Slocum projects which we will discuss more in this presentation. And I think it reflects the leadership in building a more flexible and resilient grid. Moving to the next slide, we'll talk about, so one of the key drivers behind our overall energy storage strategy is the evolving nature of winter peak demand. According to MISO's assessment, electrification is pushing total load to higher, especially during winter, while renewable generation, particularly wind and solar, is adding variability to the system. So what's interesting is while net load which is like total load minus the renewables, is declining overall. It's also becoming more volatile. And that volatility is making it harder to predict and manage those peak events, especially in winter when solar output is lower and the heating demand is high. So this is where energy storage becomes essential. Actually, it gives us the flexibility to respond quickly to those challenging conditions and smooth out the peaks and maintain reliabilities and as the grid becomes more dynamic. And to do that effectively, we need to ensure that our storage systems remain capable over time. And that will bring us to the next topic, which is battery degradation. So one of the most important and often underestimated aspects of energy storage, especially as it takes batteries, is degradation. So lithium-ion batteries don't maintain their original capacity over time. Instead, they degrade gradually due to both calendar age and their use in cycling. And these slides will illustrate 3 common approaches to managing that. So on the left, the do nothing scenario, it allows capacity to decline steadily, which can compromise performance and reliability. So you will see that the capacity falls below the capacity requirement. On the right, the overbuild strategy installs extra capacity upfront to offset those future losses, while the augment strategy adds new capacity over time to maintain performance. Now, each of these approaches has trade-offs in terms of cost, complexity, and long-term use. This is why understanding usage patterns and degradation is critical. It helps us make smarter decisions about when and how to invest in augmentation. And we'll talk about these strategies more in detail in this presentation. And moving forward to the next slide, we'll talk a little bit about degradation as well. So when we talk about battery degradation, it's important to understand that it's not just about time, it's also how battery is used. So there are 2 primary degradation mechanisms at play. One is the calendar degradation, and the other is cycling degradation. So calendar degradation happens simply due to the passage of time, even if the battery is not actively used. It's influenced by factors like temperature and state of charge and storage conditions. On the other hand, cycling degradation is tied to how often and how deeply the battery is charged and discharged. So the more aggressively we cycle a battery, the faster it wears down. Now, understanding these patterns is important because it directly impacts how much usable capacity we will have over time. And in that, it affects how we plan for augmentation. So whether we add capacity up front or incrementally over the system's life. And we will explore more of these strategies next. So in the next slide, we'll talk about the options we have. So when planning about long-term performance, we typically consider 2 main strategies: overbuild and augmentation, as we mentioned, which is overbuild, installing more capacity in the beginning so the system can degrade over time while still being above the required capacity. And augmentation is adding new capacity later in the project's life to maintain that output. So each strategy comes with some decisions. Timing is very important. So do we add capacity up front? Do we wait until the performance drops below a threshold? And coupling matters too. With DC coupling, we add new battery packs and battery racks to existing inverters, while with AC, we are installing new inverters alongside the new batteries. And in practice, the optimal strategy often blends those 2 approaches. So the right mix depends heavily on site constraints, on cost forecasts, and how the system is expected to operate. So in the next section, we will talk about how we model this option to find the most cost-effective path forward. And let's move forward. I'll pass it on to Jacob.
Thank you, Konstantinos. So before that, let's do a quick background on EPRI. So with EPRI, Bulk Energy Storage Program, We have a fairly large program covering all sorts of energy storage topics. A lot of information here, but I'm just going to move over to some kind of key summary slides. So bulk energy storage program, we're focusing on more than just electrochemical batteries. We're looking at thermal, mechanical, and chemical systems. And we have a sister program here at EPRI that's mainly focused on applications in electrochemical. Overall, we think it's important to understand all these different kinds of technologies and trying to see how they are developing and how they might work in the future system. In general, we see there's probably going to be a need for many different kinds of energy storage, just by virtue of there being different durations and thus different kind of optimal durations for these systems based off of their costs. And so we think it's important to understand how every single one is going to be contributing to the future of energy. So EPRI's approach to understanding these energy storage systems is certainly multi-pronged. I won't go through all of this just for benefit of time, but in general, we go through what I'd say is the whole swath of elements when it comes to understanding these emerging technologies. So we have a database of all the different technologies that we're tracking. This database is now towards like about 100, a little bit more than 100 different technology types. In addition, we do assessments of these technologies, understanding how they perform on paper and in practice. So you can see we do some investigation of pilot systems and how they're performing and whether that is de-risking the future development and future commercialization. We perform a lot of techno-economic analyses. This is quite important from both the cost build-up perspective, from a bottoms-up cost model of these systems, as well as looking at the potential benefits. This presentation will talk a lot about that, because it's important to understand where these technologies are in the current space to see how the market might change and how the technologies are being developed to meet those changes. Mm. And then lastly, we certainly help with some technology development. So as these systems are being put into place, we certainly help a lot with, the project planning, the different steps of verification, vetting, engineering design, etc. So back to Konstantinos, talk a little bit more about the background of this project.
Yeah, and let's talk about the two projects that we studied. So those are two cornerstone projects in DTE's energy storage portfolio. Both of them are central to our collaboration with EPRI. The first one that we see here is the Trenton Channel Energy Center. And this is a project that is transforming a 100-year-old coal-fired facility into a modern 4-hour lithium-ion energy storage system. And it's a powerful symbol of our clean energy transition because it's repurposing legacy infrastructure to support a more flexible, decarbonized grid. The Trenton Channel system will deliver about 220 megawatts and 880 megawatt hours of capacity using lithium-ion technology. And construction is already underway, and we're targeting commissioning in 2026. Now, these projects are not just about capacity, they're also about learning. They gave us a real-world opportunity to have a testbed to apply advanced modeling tools and evaluate our augmentation strategies and refine our approach to long-term storage planning. And for the next project, in the next slide, we'll see that the second project what we studied is Slocum. And the Slocum energy storage system is the second major project we studied with EPRI. It replaces aging diesel peaking units with a 4-hour lithium-ion battery system as a cleaner, more efficient solution to meeting peak demand and supporting reliability. Now, Slocum leverages the same lithium-ion technology platform as Slocum does, and it's scaled to deliver 14 megawatts and 56 megawatt hours of energy. And it was successfully powered up in January 2025. So it was a milestone in our transition away from fossil-based peaking resources. Now, together, Slocum and Trenton, they are very different but complementary case studies. One is a larger scale system, that one is a mid-sized system. So it gives the opportunity to explore how augmentation strategies can be optimized across different system profiles. And from that, we'll shift into how we model those strategies and evaluate their financial impact. So this project was designed around three main objectives. The first was to understand how different overbuild and augmentation strategies would impact key financial outcomes. So to do so, we evaluated each scenario using two primary metrics, the net present value and the internal rate of return, which we will go into further detail later. The second main objective was to optimize these strategies for real-world projects, Slocum and Trenton, each with different scales and profiles, and it allows us to test how these strategies will perform under different technical and economic conditions. And finally, we wanted to build some experience with degradation modeling, and by using tools like Storlytics, we were able to simulate how batteries degrade over time and how that affects the performance and cost. And this type of modeling is important for making informed decisions that are financially sound and about how and when to augment the batteries. And let's move forward to the next slide. I'll pass it on to Jacob again.
Thank you, Konstantinos. So here is the basic overview of our flow sheet and flow logic for doing this cost-benefit analysis. It has three major steps. So starting at step number one, and I'll try to guide you with the mouse. Hopefully you can see it. We put in our pricing information and our battery performance information into a software called Dervet. This is one of EPRI's own open source softwares that we use to optimize battery dispatch to maximize things like arbitrage revenue or ancillary service revenue. And then step two, we take that dispatch profile from Dervet and we input it into Storlytics. Now, Storlytics, certainly we're using here to model our degradation. And so not only do we need that dispatch profile, we have the model tuned to the battery, the specific battery technology that we're using, so that we can get a relatively accurate version of or scope of how that system will degrade over time, as well as the auxiliary costs associated with keeping the temperature steady. From there, we take the revenues and we take the degradation profile, and we're able to develop the net cash flows for the project. So this is including whatever augmentation or overbuild approach we're going to be taking to shore up the capacity of the system. And finally, we were able to develop that net present value and IRR, internal rate of return. So a little bit more detail here. Dervet is a price taker optimization tool. So what that means is this tool is going to be taking in an entire year of hourly price data, and it's going to optimize dispatch based off of that price data. So it will decide when to charge and when to discharge. So that's maximizing revenue potential. Given that it's a price taker rather than a price maker, the prices don't change as a result of this charging and discharging. So there is some, differences in the actual revenue that could be gained when you do charging and discharging. Given that it's a market, you're going to have some small impact on prices if you're a marginal asset. Additionally, this tool is able to co-optimize arbitrage as well as ancillary services and other kinds of services. So it's able to choose when it wants to charge and discharge within all of these different capabilities so that it's optimizing that revenue. One important thing that I'd like to say is, yes, it's of course tracking state of charge, making sure that's staying within the bounds of what's possible for the battery system. And then another thing is we have actually changed the scope of optimization. We actually call this the optimization window. so that the system is only optimizing revenue over small chunks of the year at a time. We constrained it to day chunks. So each day it's optimizing the charge and discharge. This is so that we're not overestimating some, perfect foresight where the system might be held to a high state of charge one day to then discharge another day. That can be somewhat unrealistic given especially like a short duration system. So it's not perfect foresight from the standpoint that it sees the entire year and is calculating the entire year at the same time, looking day by day. So the figure on the bottom right is showing the dispatch of a system. I'm getting some feedback from somebody's mic, so please make sure you're muted. And essentially what you're seeing in yellow is discharging and purple is charging. And the axes show on the y-axis the time throughout the day. So morning is at the top of this graph and the evening is at the bottom of this graph. And then along the x-axis you have starting from January going all the way to December. So each pixel represents an hour of the day throughout the year. So every single 8760 hours is shown here. So you can see when charging discharging occurs. So in this case, you have a system where during the winter and kind of shoulder months, we're doing a double peaking. So discharging during the morning and the evening. And then during the summer, the system discharges only in the evening. This dispatch profile, we then input into Storlytics. So I'll talk a good deal about Storlytics right now. But we use this, as I said before, to use that dispatch profile to calculate a realistic degradation profile. A lot of profiles are going on in this analysis, so please keep your dispatch and degradation straight. So what's nice about Storlytics, we're able to use all these different integrated models to understand how the battery works, how the inverter works, how the enclosure works, because all this is quite important for not only degradation, for understanding auxiliary load costs, and for making sure that things like efficiencies are being taken into account for. So a little bit more, we constructed our model using some of these integrated submodels. So the battery model, we were able to specify all of these different elements, including voltages, including resistances, including how the configuration was set up. We tuned all this to the particular OEM battery specifications. And we're luckily able to use pre-existing models for the inverter, for the enclosure, because they represented our assumed inverters and enclosures pretty well. So all these elements were set to the specific battery system that we were trying to model. So both in Slocum and Trenton case, there were some differences between those two. So it was nice to get those two accurately done. And so part of this was fine-tuning degradation to match what the OEM provided. So they provided data for battery degradation at various throughputs throughout the year, annual throughputs. So we were able to match the OEM data pretty well by fine-tuning these different stress coefficients to make sure that the degradation profile is matching up nicely. And so because we're doing this, we're able to then interpolate how other kinds of dispatch will behave in terms of degradation. So then outputs from Storlytics modeling is this battery state of health, or as I call it, degradation profile, as well as auxiliary power. Auxiliary power is quite important for understanding some additional costs that are going to come for this project. So it's certainly nice to have. This is fine-tuned, or this is based off of weather profiles for the area. So it's nice to have a representative auxiliary power for the location. Certainly it matters whether you're in a hot location, a cold location, exactly how much you should actually expect in terms of auxiliary power. And so then step 3, if you'll remember from that flow sheet, we then take the degradation profile, we put it into this augmentation planning worksheet, and through this we're able to track how the system is degrading over time. So this original system that's installed is here in this column that I'm indicating, these first 2 columns. And so then whenever that state of health or the total like energy capacity of the system is reaching our lower limit, we'll then go ahead and add in more systems as if they are augmented to the original system. So this includes battery capacity and inverter capacity. And so the total aggregate is shown here in green, and we have some nice graphs to show that as well. In this case, each augmentation is treated as a new battery system at the same rate of degradation. And then I know future versions of Storlytics are doing this even more advanced modeling to make sure it's all the perceived load is distributed among different systems. So that's a great way to see how changing loads applied to these battery systems will change degradation. So I want to go into the scenarios that we studied now. And so we studied a wide swath of them. Some of the first ones that we studied are actually different approaches to dispatch and how they might change degradation. So here I'm going to show you 2. One is maximum 1 cycle per day. This is essentially just saying there is a limit each day to how much energy can be cycled, and that's equal to what would be one full 100% to 0% back to 100% state of charge. This is actually defined as discharging, so the discharging energy coming out of the system is being tracked. And so what this does is it's going to limit what the Derivet model is able to charge within each of those optimization windows. So it's going to choose just the hours that are best suited for arbitrage. In addition, we have a variable O&M constraint. And so what this does is instead of putting what is perhaps an arbitrary, like you can only do 1 cycle per day constraint, this adds a cost to each of the hours for discharging. And so the system is only able to cycle if the difference in charging and discharging is not only positive, but also that it overcomes this threshold variable O&M. And so what that does is it's going to further constrain the hours that the system has available for charging and discharging. But if there is a day that it's good to charge or to cycle, 2 times, maybe even 3 times, given 4 hours, then they'll do that if the prices are right. And so overall, given unconstrained, maximum 1 cycle per day, and then variable O&M, you can see these different states of health over time, and they have pretty different ending points. So you can see this is fairly important to understand how the system is going to change in state of health over the project life based off of how you might change your dispatch throughout the life of the project. Total span is about, I'd say about 7-8% state of health, which is quite big. In addition to those degradation profiles and different dispatch profiles, we took a look at overbuild. So overbuild also affects some degradation. This is because you have different depths of discharge when you overbuild. So if you build out, 100 or maybe 20% extra energy capacity, then your total depth of discharge for your battery systems is going to be lower, which will have some impact on your degradation, likely reduce your degradation. So we wanted to understand how that would work, the effects on the batteries, and of course, the total project costs. We studied from the standpoint of when the next battery system would need to be installed to shore up the capacity. So in this case, we have the 1 year overbuild. This is kind of a reference case where we do mostly augmentation over the life. This is to say, augmentation occurs 1 year after the initial build. We also studied 5-year overbuild. This means we augment after 5 years of the system working. Then we did 10 years, and actually not shown here, but we also did 20-year case. Then lastly, well, not lastly, we also took a look at the frequency of augmentation. So what this means is, assuming the same overbuild, we vary how much capacity is installed during each augmentation, and thus how often you need to augment. And so here we're spanning 4 augmentations, 6 augmentations, and 8 augmentations. And Konstantinos will go into some of the cost-benefit trade-offs here when we look at the final KPI. Now, finally, we also, of course, considered different approaches, whether it's AC coupled augmentation or DC coupled augmentation. And this certainly has a deep impact when we're looking at different sizes of augmentation, different sizes of the system, whether it's a small system versus a large system, had a pretty deep impact. So look out for that when we're comparing Trenton and Slocum. In addition, we looked at mixed AC and DC augmentation, where we do a DC augmentation after each AC system is put in place, AC connected system, 1 year after. And this is to shore up some additional capacity that's available from the inverter after that initial year of degradation. You might have seen those degradation profiles. The first year was pretty steep, and so we shore that up with additional DC connected systems. Slightly reducing risk because we're not installing DC many years after, so there's some slight reduction of risk for things like voltage imbalances, for differing battery chemistries, for the sliding toys. All right, Konstantinos, go ahead and tell us about these KPI.
Absolutely. So let's talk about the financial valuation a little bit. So one of the tools we use in study is the net present value, which helps us evaluate the profitability of the investment, calculating a present value of all the future cash flows. So basically it tells us whether a project is expected to create value once we account for the time value of money. So a positive net present value means that the project is going to generate more value than it costs, when a negative one suggests the opposite. And the other important metric we used was the internal rate of return, which we show in the next slide, to evaluate the financial performance of the project. So while the net present value tells us the total value created by a project, the internal rate of return, which we can see in the next slide, it gives us the expected annual rate of return. So basically, you can think of it as the discount rate that the net present value becomes zero. And it's especially useful when comparing multiple investment options. So for this study, we calculated both of these metrics for both Slocum and Trenton, which are our 2 projects. And it helps us understand not just which strategies are profitable, but which one delivered the strongest return. So let's dive into the actual results a little bit. So for Trenton, we see that there's the net present value. What stands out is that the higher overbuild scenarios deliver the highest net present value. So it's largely due to better utilization of the investment tax credits. However, those benefits tend to plateau after the 5-year mark. And we also see that more frequent augmentations, like the 8 event scenario, outperform the reference case because they reduce the amount of capacity we expose to calendar degradation, and they benefit from those later stage discounted in the net present value calculation. Interestingly, mixed augmentation studies don't perform as strongly because the added cost of installing each segment outweighs the savings from the reducing of inverters. So overall for Trenton, this shows that a well-timed overbuild and higher frequency AC augmentation offers the best return. And the IRR shows a very similar picture in the next slide. So a higher frequency of augmentation also shows marginally higher IRR. And again, overbuild exhibits better performance. Now, mixed augmentations can provide some benefits in some scenarios as we see, but they're small and they increase the risk profile of the strategy, having to mix AC and DC augmentation. And for Slocum, in the next slide, we see quite different results actually. Because it's a smaller scale project, increasing the frequency of augmentation meant that we would have to install incomplete arrays of batteries, which results in worse than present value for AC augmentation. Now for overbuild, again, similar opportunity like a 10-year overbuild shows some increase in NPV, but it progressively declines as we overbuild for more. And that's again because of the upfront utilization of the IPCs. Now for DC augmentation, we see actually NPV increase because it avoids to install additional inverters, which is an important cost in a smaller scale project. And instead we opted to install an additional collection segment. And for the IRR for Slocum, again, same thing. Augmentation, AC augmentation exhibits progressively worse IRR as we increase the number of AC augmentations because of the additional inverters that we will have to install while not actually taking advantage of their capacity. And while the NPV is higher for the 10-year overbuild, Slocum favors a higher overbuild for an IRR perspective, and it's because it avoids future augmentation, so its long-term value streams contribute more efficiently to the return of investment. But the important thing here is to see how we can get some applicable insights, and we'll talk about them in the next slide more. It's not about the specific projects, it's about what can we get. So degradation modeling can give us some insights. It allows us to make some data-driven decisions. We're forecasting how battery performance will decline over time, and we can plan those augmentations more precisely. Not too early, so we waste capital, and not too late, which will make us risk some underperformance. And second, it allows us to run some scenarios. We can see how different usage patterns, like aggressive cycling or conservative dispatch, can affect that degradation. And finally, it can help us compare different technologies and match them better to the specific use case we have in mind. And in the next slide, again, we will recap on the levers we can pull. So one is capacity overbuild. So how much do we overbuild? How do we time our augmentation if we choose to augment? What type of augmentation, whether it's AC or DC or hybrid? And then finally, how adjusting those parameters can, as well as some operational parameters such as the limit of charge discharge cycles per year, can affect the long-term outcome of the project's capacity. And in the real world, in the next slide, it's important to reflect on all those things. So from a financial perspective, we have degradation modeling helping us with cost management, which also supports revenue optimization by aligning the usage with micro opportunities, and also helps us strengthen our investment decision. And on the system longevity side, we can extend the lifespan of the project by designing the operation strategies, improve our maintenance forecast, and enhance their reliability. So as a result of this collaboration for this project, we have gained some insights that are already shaping how we think about energy storage. And for the next slide, we'll talk about that. So for the Slocum project, we found that 10-year overbuild combined with frequent DC augmentation would be optimal for us, because we avoid to install the additional power conversion systems. But for Trenton, conversely, a larger overbuild was optimal, but we opted to use AC augmentation, which made more sense in terms of project scale and infrastructure. And we also learned that modeling degradation under different use cases can also show major differences in our financial outcomes. And while a single metric isn't enough, we learned of how combining those metrics can give us a better overall picture of what we can expect. Now, for the future, we've gained some insights, and these are already shaping our next steps. We plan to apply similar modeling to our technology selection in the future to identify the technologies better for our use cases. And we'll talk about it, I guess, in the next slide. And we're also refining our augmentation strategies, so understanding how degradation unfolds over time. Let's move to the next slide. And third, we can use all those insights to actually deploy those insights across all our portfolio. So degradation model will help us optimize that capacity for an entire portfolio. And this means smarter planning for us and more reliable performance and better alignment with our goals. Finally, as we conclude with this, and let's go to the next slide. This project has showed us that degradation modeling gives us a strategic advantage. And this collaboration with the use of Storlytics and how we collaborated with EPRI, it gave us an understanding and an ability to model with high precision than before. And it allows us to simulate some real world conditions. And it doesn't just improve our individual project outcomes, it's shaping how we plan our entire portfolio as we deploy more storage. So for all that, I want to thank all of you, and I'm really excited to learn more about this